So far we have discussed about priority queues, and today we are going to talk about heaps and heap sort as well. So implementation using heap, the sorted array implementation of priority queue, which we have seen in our earlier discussion, and it has made very sure that we can access the highest priority element quite easily by just putting it in a certain designated spot. But just to access the highest priority element, is it necessary to keep the array entirely sorted, or it would be just sufficient for it to be just kind of sorted so that after removing the highest priority element, the next one can be found from among only a few alternatives, right? So this is a very clever idea which we are going to discuss today, that is heap. A heap is a complete binary tree. I hope you remember what was a complete binary tree, and it has certain properties which we are going to see just now. But before that, this data structure heap should not be confused with the heap memory, because heap memory is where the allocation is done, some variables, data segment, your program segment. But heap is something different. If we build a heap using integer priorities, it is up to us to decide whether larger or smaller integers encode higher priority or vice versa. So if the heap that puts the smallest number at the top, we call it as a min heap, or the heap which puts the largest element at the top or the root is called the max heap, right? So we can always switch it over, but let us come back to our heap properties. What is heap property? Because we are trying to make a complete binary tree with certain property, that is the heap property. So for each node u, say any node u, the priority of the content at u, the value means the value or the priority of any content of u is at least as high as for all u's element. Just take this example. This is 8. This is also a node. This is also subtree. So this node will be greater than always 6 and 4. This node 10 will be greater than all those nodes which are below. 3 is, there is a problem because we have purposefully inserted it. So this is an illustration of a max heap. This is a complete binary tree. Why it is complete binary tree? Because up till this level this is complete or full, but from left to right, we choose it from left to right always, 2 1 1, so it is filled. So we call it as a complete binary tree. And the node with priority 3 has child to its left, which is 5, which is not we are supposed to have. So that is why I inserted it purposefully, just to tell you that what kind of exception you can have. So we are implementing a priority queue using a heap. We have already done it using sorted array, unsorted array, linked list, unsorted linked list, sorted linked list. Now we are trying to implement it through heap. So it is our responsibility to make it sure that the tree always remains a complete binary tree and heap property is maintained, which is just being told. Okay. All leaves are within at most one level of each other, which is true. All leaves, you are not having something like this, because all leaves are having, which this line says, that all leaves are within at most one level of each other, and all leaves at the lowest levels are as far left as possible. So heap can easily be sorted in an array. This is also possible because we have seen that if we start with 1, the parent will be I by 2. This is the parent number, or the index number basically, and the children will be at the index number 2i and 2i plus. But if you are you want to place it with some 0, you want to put the root at 0, then what you have to do, you have to do something like this. You have to have some addition and subtraction at this particular value. We actually added 1 to each of them. Now we assume that the binary tree is stored in some array A, which is A0, and variable size captures the number of elements currently stored in the array. So it starts with 0. What to worry about the outbound or the array size? For that, if you don't want to worry yourself, just use list data type instead of actual array. Now coming to peak, this is specifically easy. How? Since the highest priority element will always be at the root of the tree. As you have seen, this is the highest number, 10. And you can have a function tp constant root return a0. The first value will be returned. What about add? When we add an element, we need to find out where to add it. So you want to maintain the complete binary tree where this is really only one place. So a new leaf as far to the left as possible. What this means is that, okay, if I want to add a leaf, then I will start with this most leftward, then this one, then this one, then this one. This will also make our tree complete binary and fulfill our heap property. So inserting it may you can violate the heap property if the new element has a higher priority than its element. So what about removing? How to remove and how to add? So we need to fix the heap property after adding the element. First, let us see the adding element, because once you added, okay, tell me if I add say 11 here, this 11 is greater than 10, so this is not the property which we want. So we need to trickle up, means we want to take this 11 and to send it to some position where it suits or it fits this our definition of heap and complete binary tree. For that we use add. We'll increase the size because we have added. We'll give the data to a size -1, and then we'll trickle up size -1. What does this trickle up does? This trickle up uses recursive definition, and with position say which is greater than 0 and which is less than position 1 - 2, we swap them. We always swap them and recursively call. So ultimately that 11 I just showed you will find its position to the root, and 10 will trickle up or trickle down to the position where it should be. So this is how we do. What about remove? How to do remove? We have seen peak, we have seen add. What about removing? If you are trying to remove the highest priority element, our first thought would be to just delete that element from the array. Just delete it. But we can't have a tree without a root, can we have? So rather than just filling the root with one of the children that has the largest priority, we can just do it the way we have just done adding. So but what we need to do is trickling up, which I am just trying to show, that rather than trickling up, we'll do trickling down. So the improved way is to move the very last leaf to the root first. What does it mean? It means that whenever you want to delete this and keep this 2. This is the leftmost or the last leaf. Just take leaf to the root position and then apply this function which is called as trickle down. We'll see just now. So we move the very last leaf content into the root first, and that way we know that the leaf is being moved. The rest of the way, just do swap operation as we have done in trickling down. The new root will actually goes or place itself to where it belongs. So this is our function. Remove function, we swap 0 size -1. We say swap the highest priority element with the rightmost leaf, and then we decrease the size. We want to consider the former root deleted because we have just actually deleted the root, and we trickle down. How we are going to do to some position. If position is not a leaf, that is, we implement test as 2 into position plus 1 is less than size. Then we assign child of position of higher priority. That if you have only one child, what you are going to do? Return that child, or otherwise use comparison to see which has the highest priority. That is like this: if AI is greater than a position, swap this position and just trickle down. So now, hope you understood these three operations, means peak, add, remove with our priority queues implementation using heap. Now let us come to our running time of priority queue operation. As various swaps are there in our operations and returns were there, and these all are of constant time, and also the peak will be also of this order of 1 time, because it is all in array. You can just find it out because index are known. And add and remove, for this both add and remove, everything except this trickle up and trickle down will be constant time. But trickle up and trickle down, they will follow the recursive rule, and you know that whenever recursive comes, some 2 to the power I or log n will come. So the amount of work is actually order of height of the tree. So what will be the order of height of the tree? So this is the highest value, this is the lowest value. So the height will be something like this, the number of levels on the last path or last tree leaf to the root, the path in between are the levels, and this will be the height. So number of height, or the height actually will conform to the running time. So this will be of order of height of the tree, and our idea is to find the height of the complete binary tree. It is quite easy because this is binary tree. We start with one node to the level h-1. We start with 0 to say h-1. Every time it will be, level to level it will be divided or doubles it. So every time the levels are divided. So we start with this. The first one is root of course. We start with say 0 to h-2 height, and then every time, because we have this is binary, it is divided into 2. Every node has 2 children or less, means 0 or 2. So or 0, 1 or 2 means it has to be binary. 2 binary means 2. So this will be 2 to the power I. 1 is for node, and we just added this is actually 2 to the power h-1. So this is actually the geometric series, and we are aware of it. So this n is greater than or equal to 2 to the power h-1, because we are talking about that a tree of h levels has at least 2 to the power h-1 nodes, because the tree has h levels. And we can solve h just by taking log, and this will be order of n log n actually. So we have proved that the complete binary tree with n nodes has height of order of log n. And now putting all those together, which we have learned in the earlier session and this session: unsorted array for add, very good; sorted array for peek and remove, very good; but heap for add, for remove, or for peek, always very good. So this heap is clearly the best data structure to implement priority queue. So we does not want to answer now what data structure is best. Of course, heap. Now coming to heap sort. So we have an abstract data type that implements add, remove, and peek in what time? Order of log n. So do we really know any algorithm where we want to repeatedly find the largest element and remove it? Indeed we do. Look back at selection sort. We have discussed it. It was something like this. You remember this code. You start with n-1 to 0. And we see that some swapping is done depending upon the selection of proper element. So we ran the loop to find this j, but now we have something better. We can put all the elements of the array in max heap first. Rather than doing all the stuff, let's have a max heap first. So there are n elements. Each takes at most order of log n time to add, and this takes time only of order n log n. And this is very good. So we can repeatedly find the largest element and put in a final position. Finally, it takes order of 1 finding, because we need to find order of 1, and removing will take order of n log n. And since we do that in n-1 times, the whole thing takes order of n log n 2. This algorithm is called as heap sort, and it's non-recursive order of n log n algorithm, which is quite good. So when you look at it, you understand that you can actually use this array as itself as a heap. You can start with calling trickle up on each element from say I to from n-1 to 0, and the array satisfies the heap property, and we swap position 0 to n minus 1 and decrement the size by 1, then trickling down from 0. And we repeat this every time. We are putting one more element in the final position, telling the heap that it now owns one fewer element of the array. So we don't need, or we don't even need, any additional memories of the data structure. So this is quite good. So I hope you got the idea of priority queues and heap. Thank you so much. Take care.